August 6, 2025. The James Webb Space Telescope slams into emergency mode, scrambling to capture a comet that shouldn't exist. Astronomers expected a dying ball of ice. Instead, Webb's data on 3I/Atlas just confirmed a chemical nightmare. Its coma is flooded with carbon dioxide at levels never recorded and streaked with metallic nickel without a trace of iron. The experts calling in the override now admit the numbers are terrifying. This isn't some typical interstellar visitor. It's breaking every rule in the book. And the deeper the data goes, the more unthinkable it gets. Is 3I/Atlas even natural? Or is something else hurtling straight for us? The stakes only get higher from here. At 2:11 Greenwich Mean Time, the call came through. Marco Macchi's voice clipped and urgent, cutting across the quiet of the Mission Operations Center. The numbers from ground-based telescopes had just landed. 3I/Atlas was accelerating, its spectrum flashing with metals no one expected. There was no time for debate. Less than 6 minutes later, the override command sequence was uploaded to the James Webb Space Telescope. Every scheduled observation paused. For the first time in years, Webb's main science program was pushed aside by an emergency order. This wasn't a routine target of opportunity. Most targets are scheduled weeks in advance, debated by committees, weighed against the cost to other missions. Not this time. The override chain ran straight up to the project scientist's desk. Approval had to be unanimous. The risk was high. Webb's schedule is a ballet of orbits and fuel, every minute precious. One wrong maneuver, one miscalculation, and the world's most powerful observatory could lose a week of science, or worse, a critical subsystem. But the window to catch 3I/Atlas was closing. The comet's trajectory was shifting by the hour, its coma blooming with volatile gases and something else, something metallic. Macchi took the lead. His calculations, run on ESA servers, pinned down the exact coordinates. The NIRSpec instrument would need to slew fast, lock on, and start collecting spectra before the object slipped out of range. At 2:17 Greenwich Mean Time, the command was live. Webb pivoted, sensors humming as ground teams watched the telemetry stream for any sign of error. In the control room, every eye tracked the data pipeline. The first packets came down raw, uncalibrated, but enough to see the core of 3I/Atlas burning bright against the background. On the shift log, the entry is short: TU override 3I/Atlas, August 6, 2:17 Greenwich Mean Time, NIRSpec. But behind that line is a scramble that left no margin for error. Fewer than 4 such overrides have happened since Webb launched. None for an interstellar object. The tension didn't break when the data arrived, it only sharpened. What Webb caught in those first moments would upend every expectation about what a comet could be. But the chemical revelations were still to come. Carbon dioxide lines dominated the spectrum before anyone expected. At 6 astronomical units out past Jupiter, where sunlight is weak and most comets sleep, 3I/Atlas was already venting gas in sheets. Tests picked up the first hints, a faint, persistent brightening, not just a flash. Then Gemini South confirmed it, tails stretching out like a ghost limb days before the object even crossed Saturn's orbit. That's not how comets behave. In the solar system, activity kicks in closer to the sun when water ice starts to boil off. Here, the main engine was carbon dioxide, 8 times as much as water by Webb's count. The carbon dioxide to water ratio came in at 8:1. For comparison, typical comets barely reach 0.7. Even 2I/Borisov, the last interstellar visitor, hovered around half. This is off the scale. The NIRSpec instrument caught the NU3 band at 4.26 microns, strong, broad, unmistakable. Water showed up too, but as a faint afterthought. The gas wasn't just present, it was pouring out. Production rates put carbon dioxide at 8 times the water output. Dust was almost absent, making the coma thin and the tail ghostly. But the gas was undeniable. Every crosscheck, Gemini, HST, even SphereX, lined up. No calibration trick, no missed background. The numbers held. Bryce Bolin, who spent years studying interstellar messengers, put it plainly: every interstellar comet is a messenger from another star system. And by studying their light and color, we can begin to understand the diversity of worlds beyond our own. But this one's message is strange. A body that wakes up in the deep freeze, spewing carbon dioxide like a vent in the dark. The chemistry points to a birthplace nothing like our own. Maybe a world where water is scarce or where carbon dioxide is the dominant ice. Or maybe a process we've never seen, one that rewrites the rulebook for how comets form and die. The tale itself grew at a pace that stunned the teams watching live. In just days, it stretched hundreds of thousands of kilometers, driven by gases that shouldn't be active so far from the sun. The physics doesn't add up. The ratios don't match any known comet, not even the oddballs. And the further the teams looked, the more the numbers refused to settle down. But this isn't the strangest part. Webb's spectrum had deeper secrets, signatures that would send shock waves through every model of how comets are built. Nickel lines started showing up in the spectrum almost immediately after Webb locked onto 3I/Atlas. At first, the team thought it was a calibration glitch, some stray artifact from the instrument or maybe a cosmic ray hit. But the data held up. Nickel eye transitions, clear as day, stacked up across the ultraviolet and near-infrared. The numbers weren't subtle. At 3.8 astronomical units, the nickel production rate was already past 10 superscript 2 superscript 1 atoms per second. By the time the comet closed to $2.85, that number had jumped another order of magnitude. But the real shock wasn't just the presence of nickel, it was what was missing. Iron lines were nowhere to be found. Even with the Very Large Telescope's UVS instrument running at a resolving power of 80,000, the spectrum was flat in every iron channel. The upper limits came back brutal. Nickel outnumbered iron by more than 40-1. In every meteorite, every comet ever studied, nickel and iron traveled together. Your iron was a ghost. That's not normal. In solar system comets, the nickel-to-iron ratio hugs cosmic averages, 1 part nickel to 15 parts iron, give or take. The last interstellar visitor, Borisov, fit that rule, but 3I/Atlas breaks it wide open. Imagine finding a gold ring with no trace of copper or silver. That's the scale of the anomaly. Spectroscopy teams at the European Southern Observatory and the Webb Control Center went line by line through the data. They checked for contamination, for misidentified features, for solar background. Every crosscheck held. The nickel lines, 3415, 3524, 3525, 3769, 3783, 3870, 3858 angstroms, were all there stacked above the noise. The signal-to-noise was above 30 for the strongest features, but iron, not a blip. Not in the core, not in the coma, not in the tail. Lab data gave one possible path, nickel carbonyl NiCO, for a molecule so volatile it can vaporize at 43 degrees Celsius. Under the right conditions, carbon monoxide-rich ices, a dash of metallic nickel, a shot of ultraviolet, nickel carbonyl can form and drift into space, breaking down under sunlight to free atomic nickel. But iron's cousin, iron pentacarbonyl, FeCO5, is far less volatile. Its vapor pressure is low, its formation sluggish, its lines silent. That could explain the absence, if and only if the parent body was built in a world where nickel was favored and iron left behind. No solar system comet has ever shown this pattern. The near-infrared spectrograph team flagged the finding in their internal notes as without precedent in any volatile-rich body. The more the team stared at the numbers, the more the old models fell apart. What kind of formation environment could produce such a freakish ratio? Is this the fingerprint of chemistry we've never seen, or something more deliberate? The chemical puzzle only grew as the data poured in. But the strangeness didn't stop at composition. The way 3I/Atlas moved was about to raise even deeper questions. Acceleration curves started raising eyebrows before the chemical data even finished downloading. Pan-STARRS analysts tracking 3I/Atlas across a network of telescopes watched as its trajectory bent away from the expected path. The numbers weren't subtle. Over a span of just 72 hours, the object's velocity increased by nearly 0.12 meters per square second, far beyond what solar heating or gas jets could explain. That's not a rounding error. For a body 11 kilometers across, this is like seeing a cruise ship pick up speed without engines or wind. The deviations didn't follow the neat arc of gravity. Instead, each update from the ground showed a jitter, tiny sharp jumps layered on top of the main acceleration, as if something inside was flickering on and off. The Pan-STARRS team double-checked for software glitches, then called in the Minor Planet Center. All the raw astrometry held. The acceleration was real, and it wasn't coming from ice alone. Light curves added another layer of confusion. Photometric data from Gemini South and TESS revealed a periodic brightening like a lighthouse beam sweeping every 7.2 hours. That's not the slow tumble of a solid rock. The modulation was too regular, too sharp. Some tried to model it as a rotating, oddly shaped comet, but the fit was poor. Others suggested a hollow or sheet-like structure with sunlight glinting off wide, flat surfaces. Every possibility came with new problems. If the object was tumbling, its spin should be slowing as it outgassed. Instead, the period stayed locked even as the activity ramped up. Veteran observers couldn't help but recall Oumuamua. That interstellar visitor also veered off course, accelerating in ways that left physicists arguing for years. But 3I/Atlas is bigger, brighter, and its light curve is sharper, almost mechanical in its rhythm. The parallels are impossible to ignore. Some say it's a freak cosmic forge. Others whisper it could be engineered. No one can prove either theory, but the numbers keep piling up. The Pan-STARRS network logged every anomaly, feeding the data into open-access archives. The debate spilled into preprints and social media threads as astronomers worldwide pored over the acceleration graphs and brightness cycles. Each new observation chipped away at familiar explanations. The deeper they looked, the more the puzzle grew. And the next round of data would force everyone to confront possibilities that once belonged to science fiction. Ancient Egyptians shaped iron beads more than 5,000 years ago, long before anyone on Earth learned to smelt the metal. The Gerza tombs yielded these tiny cylinders, hammered thin and rolled into tubes, their surfaces pitted by centuries in the ground. Modern analysis reveals a secret. The beads are nearly 1/3 nickel, a ratio no furnace on Earth could have produced in 3200 BCE. Only meteorites falling from the sky carry that much nickel locked inside their iron. The Manchester Museum's sample, catalogued and tested, matches this cosmic fingerprint. Centuries later, a dagger was buried with Tutankhamun. Its blade, untarnished after 3,000 years, holds the same secret. X-ray fluorescence shows 11% nickel, traces of cobalt, and a chemical signature found only in iron meteorites. Scholars speak of the Widmanstatten pattern, the crystalline bands that mark a true visitor from space. The pattern itself lies hidden, untouched to preserve the artifact, but the composition leaves no doubt. This blade was forged from a fragment of a shattered world, hammered into shape for a boy king. Not just in Egypt. Across the Near East, rare beads and blades appear in royal tombs, always richer in nickel than anything smelted from the earth. Each one is a relic of a skyfall, metal delivered not by fire and ore but by catastrophe from above. Babylonian scribes watched the heavens for omens. Their tablets speak of stars that burn and stones that rain from the sky. The language is cautious, never naming iron, never describing sparks, but always warning that when the sky throws down fire, kings should beware. In their world, sky iron was a gift and a threat, a sign of favor or disaster. The Akkadian word for iron, anbar, sometimes appears in lists of precious materials, sometimes in rituals meant to ward off danger from above. Lydia Baum, historian at Heidelberg, reads these texts with a scientist's eye. She finds a pattern not in the words themselves, but in the fear that threads through centuries. When metal falls from the sky, the world changes. The Egyptians called it iron from heaven. The Babylonians wrote of burning stones and omens of war. None could know the chemistry or the true origin of the metal in their blades. But their awe and their dread echo in every analysis run today on ancient iron. The memory of sky visitors, both feared and revered, runs deep. Today's astronomers scan the heavens with telescopes, not omens. But the questions are the same. What does it mean when something arrives from beyond bearing a signature no one can explain? The puzzle of 3I/Atlas is new, but the sense of wonder and warning goes back to the dawn of history. Harvard astrophysicist Avi Loeb didn't wait for consensus. The nickel without iron puzzle, the acceleration spikes, the sharp clockwork light curve, he called them out in a single-pointed blog post. His question was blunt. What kind of natural process can make a comet behave like this? In the lab, separating nickel from iron takes industry. In the cosmos, it's supposed to be impossible. Loeb's earlier work on Oumuamua had already rattled nerves. Now he watched 3I/Atlas rack up anomalies that even seasoned comet hunters struggled to explain. Inside the Webb and Pan-STARRS teams, the mood was split. Some argued for rare chemistry, maybe a parent body forged in a carbon-rich nebula where iron stayed locked in minerals and only nickel formed volatile carbonyls. Others pointed to the erratic acceleration and regular light curve, drawing uneasy parallels to engineered objects. Loeb's critics warned against rushing to conclusions, reminding everyone how Oumuamua's oddities spawned years of debate without resolution. But the numbers wouldn't go away. The nickel-to-iron ratio wasn't just high, it was off the charts. The periodic brightening didn't match any known comet spin. And the acceleration logged in real time kept sidestepping gravity's script. Peer review threads lit up with competing models. Exotic outgassing? The carbon dioxide-rich chemistry could, in theory, drive off gassing jets, but not with this rhythm. Fractal dust clouds, maybe, but the acceleration didn't fit. A few, emboldened by Loeb's stance, floated the light sail analogy. A thin, reflective sheet built to ride on sunlight could explain both the acceleration and the sharp light curve. No one claimed proof. But the idea that 3I/Atlas might be more than a comet, that it could be a fragment of something built, not born, was no longer science fiction. It was on the table, right alongside every natural model. NASA's Planetary Defense Office quietly flagged 3I/Atlas as a high anomaly. Not a threat but a scientific wildcard. Internal risk matrices, usually reserved for objects with impact potential, now tracked an enigma. The official line stayed cautious. More data needed. Extraordinary claims demand extraordinary evidence. But in private, even the most skeptical voices admitted this object was rewriting the rulebook. The debate spilled into public forums with threads dissecting every light curve, disk and spectral line, each side pushing for answers. So here's the question. Is 3I/Atlas a cosmic fluke? A messenger from a chemistry we've never seen? Or is it the first real hint of something engineered, evidence that we are not alone? The answer, for now, hangs in the data, waiting for the next observation to tip the scale. On August 6, 2025, the James Webb Space Telescope triggered its first emergency override in years to capture 3I/Atlas, an interstellar object now confirmed to have a carbon dioxide to water ratio of 8:1, the highest measured in any comet. Spectroscopy revealed strong nickel lines with almost no iron, a composition that cannot be explained by current models. Tracking teams documented acceleration and brightness changes that defy gravity alone. These findings echo the unresolved mysteries of Oumuamua and challenge what astronomers consider natural. Despite centuries-old records of nickel-rich artifacts and omens, today's experts remain divided, some citing unknown physics, others suggesting artificial origins. Official documents list 3I/Atlas as a high anomaly, but the reasons for its behavior remain classified. The evidence is clear. 3I/Atlas does not fit any known category. Until more data is released, the true nature of this visitor, and what it might mean for our understanding of the cosmos, remains an open question.